Can you see the screen? Okay, let's see. For
I can't see
example,
it yet.
can you not see it? Okay, let me see the screen. Maybe can you see it now?
Yeah, I can see it now.
Okay, thank you. So look, suppose this is a mass. I'm giving you an example how to do the Lagrange's equation of motion. So for example, this is the mass and it is attached with a spring and also with a damper. So how are we gonna model this system? So suppose this has a stiffness K and this is moving with a displacement x displacement and it has c is the damping coefficient. So now I want to show you that how are we going to model this equation of motion using this. So let's see what is Lagrange. L what is this L stands for? L stands for kinetic energies, all the kinetic energy minus all the potential energies. So uh, and I would say kinetic energies are possessed by masses. So all the masses they have kinetic energies. In our book, K represents the kinetic energy, and P represents the potential energy. So K is half m v square, and if it is rotational, K rotational, this is half I omega square or theta dot square. Both are the kinetic energy possessed by the masses. Agreed. So now I want to show you. Usually we have in place of v, we write down. Let me rewrite another way. X dot scale. X dot is the time derivative of the position. So now look over here. The potential energy is possessed by the here the masses. When you see masses in our sketch in our sketch, so you will use the kinetic energy formula. When you see springs, you will use the potential energy due to the spring, which is half k x square, and potential energy due to the gravity. So you will sum this up together. Agree? So now you will ask me, Professor, what is this d? So d is the damping coefficient power. So power or power dissipation, the power lost. So half this is the power dissipation function. This is similar to like potential energy, but in potential energy we have x square, not the velocity square, but in differential, like sorry, this the damper, the dissipation function, it is half c x dot square. And then you will ask your professor, what is this q, what is this q, what is this q, what are you there, and what is this q? So let me explain a little bit in the formula. So when you see the formula, this q stands for the generalized coordinates. Q are the like coordinates, we call them a generalized, such as x, x dot, theta, theta dot, etc. So it completely defines the equation. So let me show you a picture of generalized coordinates here, which will tell you that how do we analyze that the motion of a particle or a mass can be completely defined by the generalized coordinate. So in the left side figure, you can see that the generalized coordinate is theta. Although we have rectangular coordinates to completely define the motion of this pendulum, but I would say replace that x and y by theta. So this is the generalized coordinate, and they completely defined by theta. So I would say r theta or xy. Both are equally acceptable to explain the position of this pendulum since it is moving in a xy plane. And how about this? So when you see two different masses, so you need to, sorry, here there is this is confusing here. So maybe I'm here you can define this by theta only, because theta is completely defining this position. Over here, r theta. I'm sorry, this one. This is also x. X is the position of the mass, and theta is the position of the. So there are two coordinates which are completely defined. This is for the mass m1, and this is for the mass m2. So let me give you one more example that will explain what um, what are the generalized coordinates. They are usually displacements or velocities. So here, so it has 2 degrees of freedom. This one has, so you can see that I need two separate degrees of freedom, which are the rotational degrees of freedom. Similarly, of this, you can just see this one and this one. They are two generalized coordinates which are completely defining each mass. So let me show you another example. So in the example on the left hand side, you see it is like a drum which is rolling on the floor. So you can either say x or theta if it is not slipping. So x is linked with theta, so like an arc length. So like delta x equals to r delta theta. Either x or maybe theta are the generalized coordinates. And for this one, this is a rope. It's a rope, and rope is has infinite number of masses. So you will have infinite number of generalized coordinates. It is known as the continuous system. So let me do one problem for you. I was trying to explain you this problem. So let's grab this problem. And let us solve this problem over here using the Lagrange's method of differential equation of motion. So I'm going to show you here. The kinetic energy to this mass is half m. This is the displacement, so I will take the derivative of this. And I'm trying to find out L. L equals to K minus P. And this is my mean position. and then you will see there is potential energy stored in this spring, so half kx square, and then the power dissipation coefficient, which is half cx dot square. And let us grab the equation of generalized equation of Lagrange's method. So Lagrange's method is defined by. So what I'm going to show you, I will consider this as each separate term. So let's do the math for this term. X dot. What is x dot? Is the velocity of this mass. Okay, agreed. So now let's do this time derivative. Or what is the partial by partial derivative with respect to velocity of this L? L is what? L is what? L is equal to half mx square minus half kx square. Agreed. So now this is my L. So let's let's differentiate this with respect to velocity. So what is that? So half is there, 2mx dot, and times the derivative of x dot, which is 1. Agreed? So now this is the, you, for the partial derivative for this term is 0 because there is no velocity variable. You agree with your professor? Now you have to take the time derivative of this component. So sorry, there is, I forgot to not to mention this, since already I already took the partial. So this is partial derivative. So can you take the double second derivative d over dt for this term? So I would say mx double dot. You are following my concern? So how am I writing mx double dot? Because I did the partial by partial derivative with respect to velocity for L, and then I have to take the time derivative of that term, which is over here. So which is mx double dot. So now let's do the next term. So the next term is half kx. So I'm gonna do this. So negative delta L over delta x. So since q is the displacement, in our case q is what? Displacement. And for this one, q dot is x dot, which is a completely defined motion of the generalized coordinates. So I would just say, so now let's do the L as partial by partial for this term, and differentiate with respect to x only. So this first term, so negative outside the first term is 0. This term partial is 0 because there is no x displacement here. So negative half is outside, k is outside, which is constant. So I would do this 2x. You agree with your professor? So negative 2 is cancelled by this 2, and then negative times negative is positive. So I'm gonna write down. So I'm gonna write down kx, positive kx. You agree with your professor? Or if you don't want to write down positive, so don't confuse yourself. So I would just write down, so I think let's keep it positive because I know this negative is making this negative as positive. So now we are left with this term. So what is this term? I'm gonna do the time, sorry, I'm gonna take the differential with respect to velocity. So can you help your professor over here is positive sign? So let's do this partial by partial v. So our x dot equals to, so our q dot equals to x double dot, sorry, x dot. So now let's do the partial derivative of the dissipation function, which is the energy of the damper. So partial by partial velocity, that's good. And now what is d? So I can do this over here as this is half cx dot square. Agreed. So now take the partial derivative here. For the 2 is a half, c is outside the parentheses of this partial, so I'm going to write down 2x dot. And again you will apply the chain rule, but x dot with respect to x dot is becomes 1, so don't worry about that one. So this is my cx dot. You agree with your professor? So now let's apply in this equation. The right hand side, there is on the right hand side, the big Q represents the forces, external forces. So imagine there is another force acting on it. F is on the right hand side. So how are you going to define? So let me write down the equation of Lagrange's method. Here I'm going to plug in all these answers here and then see what is the answer do you get. So I'm going to write down first term. What is our first term? It is mx double dot. The answer for the first term is mx double dot. Answer of the second term is cx dot. Answer of the third term is negative negative sort of plus kx. And the right answer, how many forces externally applied on this system is just F, single force. So this is equal to F. So this is completely defining the equation of motion which we get from the Newton's second law as well as from the Lagrange's method of finding the equation of motion using the generalized coordinates. Have you understood this method? Please note it down. So the next question is, I want to show you question 6.6. Let's set this. Suppose R2 equals to radius 2 equals to 2R1. This is explanation given here. So, and this given here, and mass M1 is equal to mass, sorry, this mass M1 equals to 2 times the mass, sorry, M2. The mass of the pulley is 2 times the mass of the hanging mass, which is the vertical mass here. So what I'm going to show you, look, this is like a, is moving here like a theta. I would say theta is the generalized coordinate for the pulley, and I will use this displacement as well as theta to completely define the motion. So this end is of the mass is moving. So if it is goes going down, so I'm gonna show you like this one, R2 theta. So over here, let's go ahead and start kinetic energies. So all the masses. So mass M1 and M2. So let's find out the what is the rotational kinetic energy, which is half I2 theta dot square. And another equation, the velocity of this mass. What is the kinetic energy possessed by this mass M1? So you will tell me, Professor, this is a half M1 x dot square. And now let's focus on the potential energies. We have two springs. One is this spring, one is that spring. So for this one, let's focus on this one first. This is hooked up with this small pulley. So can I write down half k x equals to r theta? And what is the arc length for this? Suppose this is arc length. So what is that arc length here? So you will tell me r1 theta square. Agreed? X is equal to, like, if it moves from here or here, whatever it is up to you. So it goes here x, infinitesimally small arc length, which is equivalent to like a straight line. So x equals to r1 times theta. This is the displacement in this spring. Agreed? Now for this spring, it is moving at both ends, so you have to consider the difference. So I would say if it is stretched, so in stretch, so I would say half k, the stretch is larger than this displacement, which is r2 theta. So I would say r2 theta. So this is the potential energy stored inside the springs and the kinetic energy. So our Lagrange says that you have to do like this. This is our Lagrange signal. So let's do for our coordinates. Q1 equals to theta and q2 equals to x. So here there are two displacements. One is the rotational, which is theta. One is translation, which is x. And q dot. Similarly, you will have we don't need q dot in this case because there is no damping coefficient. So let's focus. We have to use this generalized. Sorry, we have to use the Lagrange's method equation. So I'm gonna show you. Can we do the so okay, can we do the differential partial derivative of L? So I'm gonna show you L is, let's do the partial derivative of L with respect to x dot and then time derivative of. Agreed. So now I'm gonna show you. I'm for right now. This is Q or Q2. Let's say it's Q. Um, Q2 equals to x q2 dot. I would say q2 dot. So can we do the math here? So what I'm going to show you here. So let's do this. K equals to this term is k. This is whole. This goes to 0. And don't worry about the other terms. There is no x dot here. So how about if I do the partial q1 equals to theta? Let's do this. So let me bring this my equations here. This is my, and q1 equals to theta. So time derivative of this term. This term is what is that? So I would say partial by partial theta dot, which is I theta double dot. And then we have to do the this term. So look at here. This term here is negative L partial by partial Q Q1 x theta 1. So theta or theta I think this is theta only. So I'm gonna show you here. So so this term possesses theta, this term possesses theta. There is no theta term here. So this term is the first term k minus v. So this is 0 here. So but I can write down here for with respect to theta. So look, half k r 1 square. So 2 theta. Agreed. And for the second term, if you take the partial by partial theta, so this would be half k x minus r2 theta, and then again chain rule, you apply chain rule, so this term goes so negative r2. So this is so sorry, this I forgot to write down 2 here. This two is cancelled by this two, so this is you are left with. So let me write down the equation to collect or obtain the equation of motion here. So I'm gonna write down the equation of motion here without the damper, so we don't need to worry about the third term. So delta L over delta theta. So I'm gonna write down this term here. So the first term is Q1 theta double dot. So I'm gonna write this down here. So I theta double dot, and then minus this minus sign gets becomes positive. So I can write down here positive K R1 square minus K R2 X. So this is our equation number 1. When we consider Q1 equals to theta, this is our first generalized coordinates. So we can similarly do the math for the second term, which is Q2 equals to X. So let's do the same equation of motion here for Lagrange's method. So I'm gonna change it by not by X by theta. I'm gonna replace this by X dot and X. So X dot and X. So the way I'm gonna show you, I will take this one here and copy it here because I did some math here. So Q2 is now X here. So now look over here, this is the partial of a partial. So I'm gonna take this d over dt. So half is cancelled by this half. So you are left with m m m1 x double dot. Let me bring the k and p. They are the major things which we have to partial differentiate and then time derivative. So this is my k. So I did the partial by partial x dot. So this term goes to 0. This term is this answer. You agree with your professor? And the p, you don't have x term, so don't worry about the potential and energy here. So about this, when you take the partial L, this term. So when you take this second term here, so partial L over partial x. So you see, you don't see any x here in the first term, no x in the second term, no x in the third term. But here we have x. So we have to do the different partial derivative here. So half k. So 2 times, I would say let's put it outside. Um, okay, inside. And then multiply by partial derivative of x, which is 1. So you don't need to worry about 1. So you just write it down. So this 2 is cancelled by this 2. So you're left with k x minus r2 theta. So if you write down the equation, Lagrange's equation, so I'm gonna show you this second equation when you're using the second generalized coordinate. So how are you gonna fill in all the values here? So let me show you over here. So m1x double dot will come in the first term, m1x double dot plus kx minus kr2 theta equals to, here in the we have the force being applied here. So there is force as well. So I'm gonna add this force to the right hand side. Sorry, there is a little, here we have q. So q is big Q, sorry, big Q, which is actually the forces, external forces applied, so which is in our case is F. I'm gonna open a homework regarding these questions. First 15 problems probably you have to solve at home, uh, and then maybe a little bit more. I will show you the homework is gonna open soon for this chapter 6. Negative. The question is the negative sign is, it should be negative, right? So negative becomes positive. Yeah, I took care of that. K2x1. Did I? Okay, the question was asked, Professor, what is this? Where is this negative sign? So let me show you. This is K minus P, because this minus P is L. You see that negative sign. When you take the negative and negative, it becomes positive. Okay, so don't worry about that negative P sign. I should have written regarding the mode shapes. So let's do the mode shapes of our questions. So please drive the equation of motion. Let us do one problem before we do this problem. Uh, let's do one problem before we do this. To show you another problem. Let us do over here. Yes, do this example first. So modes and systems. So let me explain to you what do you mean by mode shapes. The mode shapes are the shapes of the displacements ratio. Like if one mass, for example, if one mass is moving with x1, other mass with x2. So what is the ratio? If, is it positive or negative? So negative or positive means like positive means if this is positive means both are moving in the same direction as a rigid body mode, same direction. If they are negative, a ratio, one is moving to the right, other one is moving to the left, so we call it a negative ratio of the displacements. So we call it as a rigid, we call it a breathing mode for the two masses. And this mode has a higher frequency. This mode happens at higher fundamental frequency, higher natural frequency. We also call it as eigen frequency. uh, and this is also at lower frequency, lower natural frequency, lower omega. I would say omega 1. Okay, got my point? So omega n1, omega n2. So whenever you see two masses, so it has omega n1 and omega n2. So we have to find out these natural frequencies through some Kramer's rule or some other 2 by 2 matrices. So let's go ahead and start one problem, and then I will explain you. You will be able to solve this problem easily. It's not difficult. I tell you, it's not difficult. When you go home, you just have to practice a little bit. And now look at this problem states. I'm skipping that questions for a moment because I want to teach you here a little bit. So this is the problem. The problem is, let me bring this problem here and find and interpret the mode ratio. You have understood what is mode ratio, that the displacement ratio of each uh, uh, individual masses. So you will see in the end you will draw like this. Let me show you over here. In the end you will draw a line, and then in the line, the displacement, for example, x1 has a displacement a1, and the other, the x2 has a displacement maybe like a2, and maybe like a1. So both are up, positive displacement, agreed? So what is a1 over a2? If you have both positive above the datum line, suppose this is the datum line. Okay, this is my datum line, and then what would you say? The ratio would be positive, agreed? And suppose the second mode, if you plug in the higher frequency, the second fundamental frequency, you will draw a datum line here. You will draw a datum line, and imagine this is positive a1, which is suppose 2 centimeter above, and this is negative a1, which is negative a2. So in this case, and this is a point where there is no motion, the node. So looking at this, this is my datum line, or looking at this shape, you will immediately say, professor, one is moving positive, like positive 2 centimeter, or negative 2 centimeter, or whatever it is. So but the, it doesn't matter whatever the magnitudes are, but the ratio is negative. You see my point? The ratio over here is positive here in this case. So we have to prove it. We have to prove it. What is that? So in this case, so first of all, you have to find out the equations of motion. Since time is limited, I'm gonna copy and paste. I'm just show you the. Let me show you the equation of motion for this case. Okay. So you will always start from the equation of motion. To find out the mode shape, you always start from the equation of motion. So look at over here. M1, when it moves to the right, the spring pushes to the left. So this is a negative sign. x1 minus x2. Agreed? And this spring also pushes to the left. And for this free body diagram, when this mass moves to the right, the spring pushes to the left with the force negative k3 x2, and this spring you will also experience, this mass will also experience the force negative k2 x2 minus, because this end is also moving, this you have to find out the net deflection in the spring, so using this equation of the free body diagram. So I'm going to show you all the forces for this mass m, all the forces for this mass m1, they are equal to mass times acceleration 1. So all the force, how many forces are acting on it? Two forces. Agreed? So I'm going to show you two forces here. So minus k1 x1 minus k2 x1 minus x2 equals to m1 x1 double dot. Agreed? This is the equation of motion for the mass m1. For the mass m2, you will do the same. M2 x2 double dot equals to, there are two forces of these two springs, so minus k3 x2 minus k2 x2 minus x1 equals to m2 x2 double dot. You agree with your professor? Now the second thing what you have to do, we have found the equation of motion, so now you have to replace this x displacement by a simple harmonic motion. X equals to e to the st. This is very convenient for us. You can ask your professor, professor, why do we have e to the theta, e to the theta can be written like cosine and sine functions. So rather than independent cosine sine, we just write down exponent, which is Euler theorem, uh, and if we, it is moving sinusoidally, so it is a very good practice to write down. So then you have to take that, because we have to take the double derivative of each this variable. So x is the displacement, you have to take the time derivative of e to the st, then derivative of s. So as as e to the st. Now you have to do the same for the second derivative. You have to do the same for the second e to the st. Now you will plug it in your equation. So what is the a? A is the amplitude of the sine of this exponent function. So after you plug in everything, so let me show you. Equation number one, you can write down like this: m1 s square plus 2k times a1 minus k a2 equals to 0. This is equation number. After you plug in x x dot x and x double dot. So for the second equation, you're gonna plug in, so m2 s square plus 2k so now the second equation. So now what you have to do, you have to write down this equation into um 2 by 2 matrix. Okay guys, so let's plug it in into 2 by 2 matrix. So make sure s it represents the, so what is the ratio? So you would see equation, I can write down here, and let me write down here. I will say a1 is, a2 is the vector, and I can write this down into 2 by 2 matrix. Matrices are multiplied by rows and columns. So if you multiply this row and column, multiply this, so you will get this equation of motion. You agree with your professor? So this equation can be written in terms of matrix by rows or and the column. So I can rewrite the second equation, can be written a negative k first, because it is You multiply negative k with a1, you get this term here. So for this term, you have to write down the coefficient of a2, which is m2 s square plus 2k. The right hand side is 0. And then the next thing which you have to do is find out the determinant. Because I'm telling you why, because this term, either this factor or this factor is 0. So but this cannot be 0, this cannot be 0, because it is moving, the both massive. So only the factor which can be 0 is the determinant of matrix, I will say matrix M. Agreed. So now what is the determinant? If you multiply these diagonal elements and negative sign cross diagonal elements, then you will find out this answer. So let me show you over here. You have to do a math here, and I'm going to show you here this equation. So how do you find the determinant? This is not difficult. When you go home, you can do it. You agree with your professor? Now my concern is, what is you have to multiply. Now can you replace s, this s square by u? The benefit of doing that, it would be a quadratic formula. So can I write down, you know that m1 and m2, they are in this question, m1 is equal to m. So I'm doing the first part first. M1 equals to m2, which is m, and k1 and k2 and k3, they're all same. Agreed? So I'm gonna show you in my next, you just have to apply the quadratic formula and find out the ratio. So I'm going to show you the quadratic formula. So that's the beauty of using replacing s square by u. So this is my s square. S square is negative k over m and negative 3 k over m. So but s square equals to u. So if you take the um, square root on both sides, so you have to take the square root of this in order to get the s root. So how many roots so you will have 4 roots here. So but you will use the real roots here. So I'm going to use this k over m, the first eigenfrequency, second eigenfrequency. So now when you plug this into the ratio, then you will get your answer. So let's do the math here. So I'm going to show you what is a1 over a2. So from this equation, can you find out? Let me do one more shape for you. Just one shape, more shape, and then you will understand. Let's do one more shape here. And can you find out from this equation of motion, can you find out what is the ratio a1 over a2? So let's do the a1 over a2. Let's do oppositely, a2 over a1. When you bring it on the right hand side, agreed, this becomes 0. This is, so I can write down a2 over a1. Now what is s square? There are two types of s square. This is s square 1, this is s square 2. So let's grab this one. As you can see, I'm sorry, this is s square is not square root k over m. Square root k over m is s only. This is s square. This is s square 2. You see my point? This is a fundamental frequency square. Oh, and this is second mode. So let's plug in for omega s square 1. So can I write down m1 negative k over m, agreed, plus 2k whole divided by k. So let's simplify this, so then you can find out the ratio. I'm gonna apply the ratio here. So m is cancelled by this m, 2k minus k becomes k, k over k is what? Plus 1. So when you see it is plus 1 with this frequency, which is the fundamental frequency, first fundamental frequency, then it means both are moving in the same direction from the datum line. A1 and A2, they are there. So let's plug in for the second fundamental higher mode. Second higher mode is this one. So let's plug in this one into this equation, into this ratio, to see what happens to the ratio A2 over A1. So let me find this out. A2 over A1 for the second fundamental frequency, higher mode, which is second higher mode. So I'm gonna write down. So M1, in place of this, I'm gonna plug in negative 3k over m. So negative 3k over m, and then plus 2k over k. Just simplify this. M is cancelled by this m. They are the same, so we have cancelled. So negative 3k plus 2k, which is negative k over k. What is that? That is negative 1. So it means that A2 and A1, they are moving with the fundament with the datum line. One is moving up, other one moving down. You agree with your professor? And if you join them, this is a node. Node means that this, if there is a spring, eh, and then there is a node between the springs. This is not moving. A node means so now when you go home, you plug in the values. We plug in the values of these these numbers. Sorry, this is yeah, these values. Oh, there are no values. They are just so when you go home, you can solve this question by yourself. So modal frequency is the frequency that each mode is related to a discrete modal frequency, resonance. We also call these natural frequencies as resonances. So let me grab this answer from the book so that you can do it at home. So I'm gonna show you this calculation. So this calculation is the one which is required in question number, I believe, 6.18, which I was trying to solve. So this is how you solve this question. So, and these are the shapes, first mode and second mode. So today we have learned about the Lagrange's method of differential equation of motion, and the second method is mode shapes. Okay. With that, I'm gonna end this lecture today. Thank you so much for attending the lecture.